NRF Itemba Labs is hosting the African Nuclear Physics Conference here in Cape Town. And as part of this conference, we have decided to host the public lecture this evening. So allow me to just briefly introduce our speaker for this evening. He is a J. Ross Macdonald Distinguished Professor and the former Department Chair of Physics and Astronomy at the University of North Carolina at Chapel Hill. He is also a nuclear astrophysicist at the Triangle University's Nuclear Laboratory. In 2014, he was awarded an Excellence in Teaching Award from University of North Carolina. And in 2015, the second edition of his book, Nuclear Physics of Stars, was published by John Wiley and Sons. In 2019, he was also the recipient of the Jesse W. Beams Research Award of the American Physical Society. So as you can pick up, he's a researcher, he's a teacher, he's passionate about stars. And this evening, we are joined via the Zoom platform. I welcome to the podium Professor Christian Iliadis, who will talk to us about cosmic furnaces and the origin of the elements. Christian, the floor is yours.
Thank you, Gillian, for the great introduction. I'm very honored to be here with you and give this public lecture. And the title is We're All Made of Stardust, Cosmic Furnaces and the Origin of the Elements. So most of you must have heard about this quote, we're all made of stardust. So my first question for you will be, where is this famous stardust quote coming from? Who said that first? So you can put the answer in the chat. Gillian will read it, or you can just say it out loud. Have you ever heard this quote before?
Well, if you ask me, I would have to sing the song.
Yeah, there's no time for that. But so a lot of people would say Carl Sagan because that's where they heard it first, or maybe other people. So I did a little bit of digging into this, and it turned out that it was first published in North Carolina. So what you see here is a map of the United States, and they're North Carolina. This is where I am at the moment. And very, very close to where I live here, maybe only an hour away by car, there was a local newspaper, the Greensboro Daily News. It doesn't exist anymore. And in this newspaper, there was a writer, Ellen Fritzl Wyckoff, who had a column there, a weekly column where one week she would educate the readers about geology and another week about biology and so on. And in this one column, she addressed astronomy. And I don't know if you can see the year. This is 1913. And let me highlight what she said there. This is the first quote I can find that, essentially says we're stardust. So in the flowery language at the time, people use at the time, she wrote, there was once a little girl who cried out with joy when she realized for one little moment that the earth is truly a heavenly body, and then no matter what is happening to us, we are really living right up among the stars. So now listen to this. The sun is made of star stuff, and the earth is made of the same material put together with a difference. And this is incredible on several levels. One level is my local newspaper doesn't have a science column anymore. I don't know about yours, but all this happened in 1913. And what is also very surprising is that the first nuclear reaction was measured by Lord Rutherford in 1919. So although this writer may not have known about the nuclear reactions and how exactly the elements are being formed, this is the first instant I could find where somebody said we're really made out of stardust. So let's talk the abundances of the elements. Famously, a colorful American writer, Harlan Ellison, said the two most common elements in the universe are hydrogen and stupidity. And if you get a little more serious, well, you will know that the two most abundant elements are really hydrogen and helium. So my next question for you is, what do you think is the third most abundant element in the universe? Just throw out some wild guesses. Don't be shy.
Carbon.
Okay, because I'm not getting any answers, let me go. Is there any suggestion?
Carbon.
Silicon.
There's
Silicon.
carbon.
Ah, very good guesses. Very good. So let's have a look at this. If you're an astronomer, the answer to my question is oxygen. Carbon is very close. So an astronomer looks at the abundance of the elements in the universe like this. Mostly it's hydrogen, and then helium, and then the next slice is oxygen, and everything else is in this tiny other little slice. Now, if you are a geologist, then what matters most to you is what the abundance are on the Earth's crust. And there, oxygen is by far the most abundant, and then silicon, that's what some of you said, and then next aluminum and iron and so on. If you're a biologist and you ask the question, what elements does life depend on, then oxygen is in the majority there, and then there's carbon, hydrogen, and so on. So we need to talk about what do atoms look like. So I don't know about you, I like coffee, good coffee. So I walked around the other day and then I saw this coffee shop. It's called Atomic Coffee, and it had a model of an atom in its logo. And our question is, how do we visualize atoms? And what you see here is three black dots that move in planetary orbits around something in the center. So this is really a rough model of the atom. And it says you're saving mankind one cup at a time. So I really, really like this. Now, I have to tell you, we'll talk a little bit. I will try to refresh your high school chemistry, but I have to tell you, this is really the world's worst atom image. So if you remember what is moving outside there, these are electrons and they're negatively charged. And then in the middle where you see this coffee cup, that's where the atomic nucleus is. And the atomic nucleus consists of protons, they're positively charged, and neutrons. As their name says, they're neutral. So what is wrong with this image is two things. First of all, the electrons don't move on little planetary orbits. And this was a revolution in physics. And the first, or one of the people who came up with the key ideas was Erwin Schrödinger, an Austrian physicist, and he received the Nobel Prize in 1933 for his contributions to this new theory at the time of quantum mechanics. So quantum mechanics tells us that in the microcosm, we cannot talk about planetary orbits. Elementary particles like electrons and protons, they behave completely differently. So this is how you would visualize an atom. If you could be in a tiny spaceship and approach a hydrogen atom, then this is what you see. You would see, if you look, the electron maybe at one location. And if you look again, it's at another location. And if you look again at yet another location, but it's not moving between these locations on paths. So we may not talk about anymore about paths, and all we can say is a probability of finding the electron somewhere in space when we look at it. That's the first thing, what's wrong with the logo on the left. The second thing that's wrong, and that is repeated in almost all chemistry books, is the scale. The scale, there's a difference, although in the middle here, in the image on the right, there's a black dot and it's relatively large. In reality, the atomic nucleus in the middle is tiny compared to the size of the atom. There's a size difference between the diameter of the atom and the diameter of the atomic nucleus by a factor of 100,000. If I would plot here or show the atomic nucleus as a black dot on this scale here, you wouldn't see it. It would be so small. So the atomic nucleus again consists of two elementary particles, protons that are positively charged, and neutrons. This field I'm working on, called nuclear astrophysics, started with the question, what powers the sun and keeps us alive? There are lots of theories. What is happening here? Are these chemical reactions? Is the sun gravitationally contracting? Is that the energy where it's coming from? And it was pretty clear in the 1920s already that the only possible energy source large enough is nuclear reactions, nuclear fusion. But how this is exactly happening, that wasn't clear because the nuclear physics wasn't known that well in the 1920s and early 1930s. So the first people who really understood what's happening in the sun is Carl Friedrich von Weizsäcker in Germany, and then Hans Bethe and his graduate student Charles Critchfield. And the important papers they wrote at the end of the 1930s. And the Nobel Prize for this work went to Hans Bethe in 1967. So they were the first who explained how hydrogen is being fused in the core of the sun and is becoming helium. Now think about this. In a nuclear reaction, like hydrogen is fusing to helium, you always change the identity of the elements. This is an alchemist's dream, to make gold out of lead or something like that. This is not what's happening in any chemical reaction. This is only happening in nuclear reactions, when atomic nuclei fuse. So this fusion of hydrogen, that's just a proton, to helium, the helium nucleus consists of two protons and two neutrons, shown here in the middle, the two red and the two blue spheres. People thought initially, well, they just come together and then that's the fusion. But this would be a process involving four protons that come together in the hot stellar plasma at the same time and same location, and the probability for that to occur is way too small. And this is why it took so long to understand how this fusion is really happening. It's happening in three steps. Because this is so important, I will walk you through the three steps. These are three nuclear reactions. This is shown over and over. So this is the first step. Two protons are fusing together and becoming deuterium. What's moving away here with the red and the blue dot, this is a chemical form of hydrogen, but it's heavier than hydrogen. It has an extra neutron. So it's called deuterium. This is the first step of what's happening in the sun. In the second step, you have this deuterium moving around in the stellar plasma and is fusing with another proton. And that gives rise to a variety of helium, not quite the helium we're after, that's shown on the left, but it's called helium-3. It has two protons and one neutron. And in the final step, you have two of these helium-3 nuclei, and they fuse together to become helium-4. This is how the sun produces its energy, and this is what keeps us alive. So I really haven't explained to you where the energy really is coming from. I explained to you what these nuclear reactions are, but where is the energy coming from? So let's have a look at this animation of the Tsar bomber. This was, people think, the largest hydrogen bomb that the Soviet Union exploded in 1961. And some people say its explosion power, the energy released, corresponded to 50 megatons of a chemical explosive, TNT. But it's not clear, may have been even larger. So I'm showing this to you because what's happening in stars, either under controlled conditions in the sun or in stellar explosions, is very similar to what's happening in this explosion here. The person who explained where all this energy is coming from was Albert Einstein, who received the Nobel Prize in 1921, one of the geniuses in all of science. And his famous equation, E is equal mc squared, really explained where this is coming from. What is this equation? What does it say? The E stands for energy, m stands for mass. And the only other quantity in this equation is a natural constant, the speed of light. This is has the same value everywhere in the universe. And because other than energy and mass, there's only the speed of light in this equation, we say that the meaning of this equation is that energy is equivalent to mass. It's not the same as different units, but it's equivalent, meaning in principle, energy can be transformed to mass, and mass can be transformed to energy. The second meaning of this equation is the speed of light is a very large number, 300,000 kilometers per second. But what you see in this equation is not just the speed of light c, but c squared. This becomes an even larger number, meaning if you start out with very little mass and you multiply it by a huge number, you obtain a lot of energy. And this is exactly what's happening in the sun. But let's just rearrange this equation. Let's solve for mass. And let's ask the question, in this Tsar Bomba, if mass was converted to energy, what was the mass that was converted in that explosion? So we find it by rearranging this equation, and we put in 50 megatons of TNT, and we divide by the speed of light squared, and we find that it's about 2.5 kilogram. That's the mass of the laptop I'm giving this presentation on. And what's happening in the sun, I told you about these processes, fusion of 4 protons to 1 helium nucleus. And it turns out that the helium nucleus is slightly lighter, slightly less mass than the sum of all protons. So this is the mass that is converted to energy and that powers the sun and keeps us alive. The sun converts each second 4 million tons of mass to energy. So I don't know what your plans are for the weekend, but maybe the sun may run out of hydrogen fuel and they will not be shining, but the mass of the sun is huge compared to this number of 4 million tons. And it will shine for another 5 billion years. So you don't need to worry about your weekend plans. I'm coming now to the most stunning effect. This is really what I need to tell you about if you ask me these nuclear reactions, how do they proceed? The first nuclear reaction I told you about, the fusion of 2 protons to deuterium, well, the 2 protons, they're positively charged. And if you remember, like charges, they will repel each other. Now, the second reaction that I showed you, deuterium fusion with protons, same thing. You have 2 atomic nuclei that are both positively charged. They don't want to fuse. They will repel each other. There shouldn't be any fusion. There shouldn't be any elements other than hydrogen in the entire universe. So what is happening here? What's going on? So I found this video online. I will show you. This is my favorite sports, football or soccer, how it's called in the United States. And what this boy does, he just kicks the ball against the wall. So to prove that soccer really is my favorite sport, I dug out a picture for you. This was taken in 1973. On the right is my father. In the middle, that's me. And so I grew up in Germany. My parents were foreign workers working in German factories. And there were a lot of Greeks at the time in Germany working in these factories, and they formed their own soccer team, their own football team. It was the only football team of foreign players playing in this German league. So my father would take me every week to watch these games. And I can tell you, I have some very fond memories of, this only foreign team playing with all these other German teams. So why am I telling you all this? My childhood experiences, all that. What if I tell you that there is a finite chance that when the boy kicks the ball against the wall, that the ball would just go straight through the wall without breaking it? I'm not saying that the boy will kick the ball over the wall. Again, like when he hits the wall, there's a finite chance the ball will go right through without doing anything to the ball and without breaking the wall. This, for me, is the most stunning effect. Now, if you calculate the probability, and this semester, just 2 weeks ago, I had my students calculate this probability for a soccer ball, it's tiny. It's very, very small. But when you get to objects like electrons and protons, then these probabilities become much, much larger. This is called quantum tunneling. It was discovered by a German theoretical physicist, Friedrich Hund, and the first person who applied it to explain alpha radioactivity was George Gamow. So at this point, when I give public talks, some people in the audience will say, yeah, this is just a nice theory, but how do we know this is really happening in reality? And if you think that way, I will tell you, you should not be using your cell phones, because cell phones flash memory. The information is stored again on floating gates by putting electrons in little regions on the chip. And this movement of the electrons only works by quantum tunneling. So people who think that quantum tunneling is just science fiction or something, they should not be using their cell phones. So this is happening in nuclear reactions in stars and in the sun. They always proceed by quantum tunneling. Otherwise, they would repel each other. There would be no nuclear fusion. Everything started 13.7 billion years ago with the Big Bang. So this story has been told many, many times. Arno Penzias and Robert Wilson, they received the Nobel Prize for their work in 1978. They were working on detecting very weak signals of the very first communication satellites at the time. The signals, and these are the first satellites, the signals were very weak, and they built this huge horn antenna to measure the radio signals from these satellites. It was important for them to suppress all background. And they saw that there was a background that they could not suppress, and this was radio waves of about 1 millimeter wavelength, so in the microwave region, that seem to arrive from all directions isotropically. And the story, how they thought at some point that birds are nesting in the horn antenna and all of this, I do not know if that's really true. But this was the birth of the discovery of what we call the cosmic microwave background radiation. And it turned out that this radiation is a relic from the Big Bang. And again, sometimes when I give public talks, people say, yeah, Big Bang, but there must be other theories, just a theory. We have no other explanation for this microwave background radiation. This is the only theory we have. So a few years later, people pointed out immediately that yes, the radiation is isotropically coming from all directions to us, to Earth, but there must be some tiny, tiny fluctuations on a level of 1 in 100,000 in this microwave wavelength. And what this shows is an image of a satellite, the COBE satellite, that was launched to measure these fluctuations. So this is an all-sky image, and you see green and blue regions here. And for this work, John Mather and George Smoot received the Nobel Prize in 2006. This is very, very important because this picture tells you how matter was distributed about 380,000 years after the Big Bang. That was the time when the universe became transparent to electromagnetic radiation. So this is the photons that we see. This is so important that another $1 billion of taxpayers' money was spent on a follow-up mission. This is actually the second follow-up mission, the Planck satellite in 2009, and you see how much better the observations became and how much more detail you see in 2009 compared to 1989. These measurements made cosmology, the field of cosmology, a precision science. When you read the universe is 13.7 billion years old with a tiny error bar, and then there is that much matter, and there's this much dark matter, and there's this much dark energy. All of this, we conclude by the analysis of these fluctuations in these images that you see. That's why this is so important. There's no other theory that can explain any of this. So let's talk about matter and antimatter. Well, I'll talk about antimatter, but I really like this cartoon here. It says, after the discovery of antimatter and dark matter, we have just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. It is funny, but it also has a true core in that we'll talk about antimatter in a minute, but if you would ask me, well, what is dark matter? We know that it's there from its effect, its gravitational effect, but we don't know what it is. And this is an area of active research. So a snapshot of the early universe, if you ask me, how shall we visualize the early universe 100 seconds after the Big Bang? How did things look like? I like to look at a bubble chamber image. Bubble chambers were huge in the 60s and 70s because elementary particles, they're so tiny you cannot see them. But a bubble chamber that consists of a superheated liquid, and like airplanes create these condensation trails. If elementary particles move through the superheated liquid, then they create along their path these bubbles. So now visually, with the eye, you can see the tracks of these elementary particles. So for the discovery of, for the first person who built a bubble chamber was Donald Glaser, and he received the Nobel Prize for this invention in 1960. Let's look closer what's a lot of stuff is happening here. So right here, you have, I don't know if you can see my mouse here, but you start out, and there are no tracks up to this point, and then you have two tracks, they're bending in opposite directions. Bubble chambers usually are placed in magnetic fields so that you can distinguish particles of different charge. So you have now two tracks that bend the same way, but in opposite directions. But you didn't have anything before this point there. So clearly what you see here is the production of a matter-antimatter pair out of pure energy. So what you see is that energy disappears and is converted to particles. Remember what I told you about E is equal mc squared, exactly what this equation predicts. And you can also find other instances in this image where particles disappear and are converted to energy. Let's be a little more precise. The laws of physics tell us that when particles are created, they appear always as particle-antiparticle pairs. You cannot convert energy into two protons. That is not possible. So it must be a proton and an antiproton. If you try to convert matter to energy, then the only process we know of that converts that matter entirely is when particles and antiparticles completely annihilate. So two protons will not, you cannot convert them easily into energy. But if a proton collides with an antiproton, then these particles disappear and their mass is converted entirely to energy. So it turns out that for 1 billion proton-antiproton pairs, there's one extra proton. So in the early universe, if you had 1 billion proton-antiproton pairs, and they all annihilate and produced energy, and if this would be the end of the story, there would be no elements in the universe. It would just be energy. No matter would there be in the universe, no different elements, just energy. But there's a tiny imbalance. There's one extra proton among 1 billion proton-antiproton pairs. And this imbalance is still unexplained and is an active research area. A lot of people are trying to find out why is this imbalance there that gives rise to all this matter in the universe and the matter we consist of, for example. Cosmic history on one slide. So we start with the Big Bang on the left. Then 100 seconds after the Big Bang, the first nuclear reactions occur, but then they stop because the universe expands, it becomes cooler, and no nuclear reactions keys. Then 300,000 years later, this is when atoms form from free electrons and protons. This is where the baby picture of the universe is coming from that I told you about. 300 million years after the Big Bang, the first stars form. And then sometime later, the first galaxies form. 9 billion years after the Big Bang, the solar system formed. And 13.7 billion years after the Big Bang, this is where we are today. Nuclear reactions, I told you already, in a very narrow window lasting only 100 seconds after the Big Bang, we have nuclear reactions. And they produce hydrogen and helium, and that's about it, and very little lithium. And then 300 million years after the Big Bang, this is when stars formed. So this is where nuclear reactions have occurred and are still occurring inside stars by different means. I will tell you about. So the first people who really understood what is going on is the Burbages, Margaret and Jeffrey, and then Willie Fowler and Fred Hoyle, and independently Al Cameron. In this paper that published in 1957, it's one of the most cited papers in all of physics, and it's called The Synthesis of the Elements in Stars. And they were really the first who explained in this paper how different stars fuse different elements in their interiors during their lifetime or during their explosions. So you shouldn't think that all the elements are made in each star, but different elements are made in different stars by completely different nuclear physics processes. And this was one of the foundational papers of the field of nuclear astrophysics. This is a great visualization of what is happening. And what I will show you here is a simulation, a supercomputer simulation that starts out with 20,000 solar mass molecular cloud. And this molecular cloud consists only of hydrogen and helium. There are no stars in here. And what these researchers from Northwestern University did, they built a computer model, and this is the starting point, a cloud consisting of hydrogen and helium. And they put the best physics that we know in their simulations, the best hydrodynamics and thermodynamics and atomic physics and nuclear physics. What you will see here is this gas cloud that has initially no stars. Well, you always have motion in this gas cloud, and you will have chaotic motion. And then by chance, you will have regions in this gas cloud that become a little denser up to the point where gravity is taking over and it's pulling this region together. In this region, the temperature increases up to the point where the temperature is large enough for nuclear reactions to occur. And this is when stars are born. So we say a star is born when there is a gas region that has a high enough temperature to ignite nuclear reactions. So let me show you the simulation. At some point, you will start seeing these white dots. These are stars that are born. And these stars, each of these will evolve, and they will fuse elements in their interiors by nuclear reactions. And if they're massive stars, they evolve fast. So you can see how they eject matter. All the elements that were fused in these particular stars, all these are now ejected into this cloud. But star formation still goes on. So the new stars, they form out of matter that was polluted by the previous generation of stars. So the matter we consist of, the solar system consists of, that underwent this cosmic cycling many, many times. Okay, so let me tell you a little bit about stars. So we talked about the sun already. Betelgeuse, not to scale, is actually much, much larger than the sun. It's a red supergiant. It has completely different fusion processes in its core compared to the sun. The sun fuses hydrogen to helium, as we discussed. Betelgeuse in its core fuses helium to carbon and oxygen. And it produces also other elements. Mira is a variable star in an advanced stage of evolution. Our sun will become something like this in about 5 billion years. So again, it does something very different in its interior. And these variable stars, slightly later in their lives, they produce these planetary nebulas. You may have seen, here's a famous example, the Cat's Eye Nebula. And the sun will produce something like a planetary nebula. We don't know how it will look like, but that's what it's predicted to do. Then we have stellar explosions, the famous Crab Nebula, the result of a massive star explosion. So this was a star like Betelgeuse, about 15 times as massive as the sun. And it exploded and produced lots of different elements by fusion reactions. Then there are other types of explosions. They're called classical novae that you can see here. Beautiful example, Nova Cygni 1992. Then there are other types of supernovae. So I told you about the Crab Nebula and massive star explosions. We call those supernovae. But Tycho's supernova, discovered in the 16th century, is a completely different phenomenon. It's not the explosion of a massive star, but it's a stellar explosion that occurs in a binary star system. And finally, we have colliding neutron stars, and a lot of elements are also synthesized in these events. All of these are real images, like from the Hubble Space Telescope and so on, except the last one of colliding neutron stars. This is an artist conception. The key message to take away here is that stardust from all of these phenomena contributed to the matter we consist of. So let me tell you, I will just focus on the 19 elements that are essential for life as we know it. I will tell you where they're coming from according to our latest research, the state of the art in our field. Hydrogen, I already said, is made in the Big Bang. The Big Bang also makes helium, but I'm only focusing here on elements essential for life. Helium is not essential for life. Then stars like Betelgeuse, the massive supergiants, before they explode, they make elements like oxygen, phosphorus, carbon, nitrogen, magnesium. In our solar system, all of the oxygen we breathe was synthesized in these massive stars before they exploded. When they explode, so again, there's a Crab Nebula, the supernova remnant, they make calcium, iron, sulfur. So all the calcium in our bones is predicted that it's made during the explosion of massive stars. These other type of supernovae, they mostly make elements in the iron region. So half of the iron in our blood cells, for example, is made in these events. And then these low or intermediate mass stars, we call them AGB stars, asymptotic giant branch stars, they make the other half of the carbon and nitrogen that we consist of, and they make all of the molybdenum. And finally, the neutron star collisions, they make the iodine that is crucial for the working of our thyroids and half of the selenium. So I have to tell you a little bit about my work just on one slide. I will not bore you, but I work at the Triangle University's nuclear laboratory, located in North Carolina. And we have a number of different ion accelerators. This is how we measure fusion reactions in stars. So here's some images. So when you measure a fusion reaction, and of course the fusion of protons with deuterium, the things that I mentioned, these are known for a long time. And what we're interested in, because remember, I said different stars produce different elements, and there's so many different nuclear reactions that take place in any of these scenarios that I showed you. So we're measuring in the laboratory much more complex nuclear reactions. So say we would like to study the fusion of hydrogen with aluminum. Then we need to produce an ion beam of protons, that's the hydrogen, and we need to direct that on a piece of aluminum. And that's how we study the fusion of these atomic nuclei. So that's why we're dealing a lot with ion accelerators. So what you see here is our graduate students working with the accelerators. We don't have operators, so the students, they learn about, they become experts in high voltage systems and vacuum systems and electronics and so on. The key here, when I meet people and they say, "What are you doing?" I say, "Well, I'm a nuclear astrophysicist." A lot of them say, "Oh, you're going to CERN and Fermi Lab," and because they think stars are very large, and they're very hot, and very, very high energies, but it's exactly the opposite. The Even these high temperatures in stars, what they translate to in terms of energies, very, very low energies. So our measurements is not at very high energies, at low energies, but the key is we need to produce these ion beams of very, very high intensity. And the students, I told you, we don't have operators, they need to steer the beam, the ion beam on target. And if you're really not careful, the beam is so intense, if you have a milliamp of protons, it acts like a blowtorch and it will melt the beamline. This is a stainless steel beamline part was melted here because we have not been careful with how we steer the beam. So I will end here, but although Carl Sagan was not the first, came up with the Stardust quote, but it's his what he said in detail. This is the most famous one. I would like to end with this. He said, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We're made of star stuff." Thank you.
Right. Thank you very, very much, Christian. Thank you for taking us on that fascinating journey, highlighting the fact that there's a lot of time and energy that went into constructing these models. But there were a lot of words that you mentioned, fusion, equivalence. We shouldn't worry about the weekend. Apparently, the sun will still be alive. We can learn from soccer because if we play soccer, who knows? We might end up being an astrophysicist. You gave us the age of the universe, 13.7 billion years. Talked about matter and antimatter and dark matter, the fact that stars are born. But yeah, lots of stuff that you threw at us. So let me open up the conversation to our audience. So ladies and gents, if you have questions, you can either pop them in the chat, or if you just want to raise your hand, I can acknowledge you. Then we can open your microphone and you could just ask the question to Christian. But thanks again for your enlightening talk in terms of just taking us on this fascinating journey. All right, so I'm checking the chat. I don't see anything there, but if you have a question, please do raise your hand and then we'll just acknowledge you and you can ask your question. All right, maybe while we wait, Christian, I mean, you were giving us that periodic table. JJ, I'll be with you just now. So you indicated that different stars, in a sense, contribute to different parts of that periodic table. Is that why we find different stable isotopes?
Yeah, as I said, the elements, they're made in different stars. So what I just focused on are the elements. I mean, they're all stable. That's what I focused on. I just focused on the ones that life depends on. But I can show you if you want. I can show you the origin of all elements of the entire periodic system. But it
Wow.
would be more complicated. And I didn't want to overwhelm you
Okay.
with information. But yeah.
All right. Let me go to JJ. JJ, please do ask your question.
Thank you. Thank you, Gillian. Thank you, Christian. I was looking at the time when you said I'm done, and it was 40 minutes, 45 minutes. So well done. You kept our attention, and I was really riveted to the screen. Uh, you mentioned that people think because you're a nuclear astrophysicist, you are probably working at telescopes, but in fact, you're working in labs with beamlines and things. So my quick question was, who trains your students to know what to do in a sophisticated nuclear physics lab with detectors and beamlines and vacuum systems and high voltage? Are you training them? Do they train themselves? How do their training work?
Well, this is our responsibility as their advisors to train them. And so it's a combination things, how to fix a vacuum pump. I don't have to train them because we have technicians in the laboratory. That
Oh,
saves me a lot of time. But so all the higher level stuff, then that's our responsibility to make sure they learn all this. When our students see labs like mine, and ITHEMBA is probably very similar, they become unique in the world because the training our students get, you don't get that at the larger facilities anymore. It's the way astronomy went decades ago. I
yeah,
had students who switched from astronomy to me because they thought they go to a telescope and then they do all
yeah,
these. No, they don't do anything. They don't go anywhere. They just sit at home and then everything observing is remotely. And nuclear physics is going the same way as high energy physics. And I don't like it that the smaller labs are disappearing because this hands-on training that we provide, I didn't tell you about even the target tree. They need to make their own
yeah,
targets and all that.
yeah,
And yeah, so when our students finish, they get
yeah,
very good offers from national labs and private industry and so on. And
yeah.
I really regret it that this is slowly diminishing.
Mm, mm. Thanks for
Right.
that.
Cool. There's just a question in the auditorium at NRF Timber Lab. So, Wendy, if you can get the person who just asked the question. All right, we don't hear you in the auditorium yet. Right, while we wait for that, I'm just going to look at some of the questions in the chat. All right.
Okay. Can you hear
Yeah,
us?
I can hear you. Go ahead.
Awesome. So I usually get questions when you try and explain to people that elements are formed in stars. Then they usually ask to say, what about the elements we have here on Earth? Where do they originate? How do we link them to the ones that are currently being formed? Or how do we relate the elements we have here to the Big Bang? So maybe you can clear that mystery. For me, as I try to explain it to them, because I usually assign the elements we have here to the origin from the Big Bang.
Now, Christian, I don't know if you got that.
No, I didn't get the question clearly, but there may be some misunderstanding. So when I showed you the molecular cloud, this is what's happening before the solar system formed. And our solar system formed exactly in a cloud like that, that underwent cosmic cycling many times. And when I say cosmic cycling, that meant that in this cloud, many different type of stars formed. And some ejected carbon and nitrogen, and others iron, and others iodine, and so on into this molecular cloud. And out of that matter, the solar system formed. That's why I said the elements life, our cells consist of, they're really coming from these processes that happened before the solar system formed.
Yeah, so am I correct in trying, just picking up on what the question was, that in essence it's important to understand that the Earth was formed during that same process.
Yeah, exactly.
Yeah.
Together with the stars, of course, the planets form.
Yeah.
And this is exactly what happened to our solar system.
All right, then just here in the chat, there's a question from Craig. Can you say a little bit more about how the input from nuclear physics experiments are analyzed to accurately estimate elemental abundances?
Yeah, this is a complicated question that requires really a longer answer, but let me just tell you what we do in our lab. And other groups do different things, but we measure the nuclear reaction cross sections. And we do that because we would like to calculate from the cross sections the thermonuclear reaction rate. What this is the number of nuclear reactions that occur of a given type in the stellar plasma per unit time and per unit volume. And so if you have a collection, a library of all these thermonuclear reaction rates among 10,000s of different nuclear processes, that is the nuclear physics input you need to simulate stars.
All right, and then just a question of clarity that comes from Peter. I don't know if is it 3I Atlas or 3L Atlas? He just wants to know whether that is important to your work.
I do not know what 3I Atlas is. If you could explain that to me, then I will give you an answer.
Yeah, Peter, maybe if you can just unmute.
Okay, so there is this comet moving through our galaxy at the moment. So everyone on YouTube, things that I'm seeing is they are tracking the movement of this comet. Are you guys even interested in this movement of this body through our galaxy?
No, we're not interested in that. Our interest in meteoritics is the embedded micro-size pre-solar grains. That is our interest in meteorites. So what these little pre-solar grains are, they're actually stardust grains. And so when I said earlier that the solar system formed out of matter that underwent this cycling, this cosmic cycling, the implicit assumption is that when the solar system formed, it was so hot, everything became homogenized, and you cannot really tell which parts in this solar cloud came from which previous star. It's too complicated. But in primitive meteorites, we find these tiny inclusions, and they're called pre-solar grains. They did not take part in this homogeneous process. They come straight out of those stars. They reflect the isotopic and elemental composition of what was formed in these stars prior to the formation of the solar system. That is our interest in meteoritics, not the movement of asteroids through the solar system.
All right, and then just here from Anil, what releases more energy, nuclear fusion or nuclear fission?
So the textbook example, you see the binding energy per nucleon curve, which starts low with hydrogen and helium, then increases quickly, it peaks at iron, and then it declines slowly. This is usually used to explain that nuclear fusion produces much more energy than nuclear fission. That's why hydrogen bomb explosions are a factor 1,000 stronger than atomic bomb fission type explosions. But it then depends on the specific reactions. There are nuclear fusion reactions that don't generate much energy. It depends. But in general, fusion generates much more energy than fission per nucleon.
All right, and then maybe just a follow-up from the same person. We measure gravitational presence of dark matter, but we do not detect it. Does that suggest that there's some fundamental physics that's missing?
Yes, and I'm not an expert, I'm not working in this field, but yes, there are some people who think dark matter, this is some exotic new particles that we don't know of yet. So this is huge in particle physics. There are other people who say, no, 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 this is not any particle. This is just, we need to change our understanding of gravity, that it may have changed over time, the gravitational constant. That's very important too. There are all sorts of ideas out there. Clearly, something is fundamentally missing in our understanding of nature. And this is always interesting. We'll always learn by doing that.
All right, let me just check. Any other questions, colleagues, either in the chat or if you want to just raise your hand? Christian, maybe if I can ask you, I mean, you mentioned the age of the universe. I mean, how do we get to that number?
Yeah, as I told you, these fluctuations in the microwave background radiation, if you analyze, this is a very complicated analysis, but if you analyze these fluctuations, you get all sorts of information out, among them the age of the universe. I mean, the error bar is tiny, it's incredible. And apart from that, you get information about dark energy and dark matter and many other cosmological parameters. These observations, they really made cosmology, which was more of a speculative field, made it into a precision science.
All right.
We
Right,
have
let me
one
just
more.
one more question in the auditorium. Please, Wendy.
Yeah, unfortunately, someone took my question about 3I Atlas comet because I wanted to ask you, because since you are calculating some elements from space, the comet must be a good site for you to do some new element discoveries and understanding. I don't know if why you neglect the calculations from comets surfaces and other things from there.
Yeah, it turns out that this is not really very interesting. The comet compositions, these are very well known spectroscopically. We know what's in there. There's no new unknown element in a comet or in an asteroid. So what's much more interesting are regions that we can measure spectroscopically around hot stars. That's where we see interesting element ratios and interesting isotopic ratios, but not so much in comets and asteroids. We know their composition very well. There's no hidden new element in those.
All right, so let me just check.
Another one, Gillian.
Yes, please, to go.
Yes, thank you. Thank you for the good talk. I first a comment and then a kind of a question, just curious on my part, since you showed us an interesting slide with the soccer ball. The other equipment that shows that quantum mechanical tunneling really works is called the STM, the scanning tunneling microscope. But my question is, since you took the theory further with that football example, I'm interested to know what the probability was. You said your students did calculation to calculate the probability of that soccer ball going through the wall. What was the answer?
Yeah, so let me tell you, first of all, I will tell you a little story. When I was in high school in Germany, I still remember my physics teacher telling us we will never, ever, ever, never. And if somebody says that, you already know they're probably wrong, but you will never, ever be able to image single atoms. And already in 1986, the Nobel Prize was given to a group that invented the tunneling microscopes with which we can image single atoms. So it's an incredible achievement. So a number more Nobel Prizes were given for quantum tunneling, mostly to condensed matter. But your question, yeah, so we calculated this probability. So I was teaching quantum mechanics using the WKB theory, and this probability is about 10 to the minus 10 to the 35. So there are two exponents in this expression. You can easily calculate that if you kick the soccer ball every second since the beginning of the universe against the wall, this quantum tunneling would not occur. It's way too unlikely. But the point why I showed it is the probability even from macroscopic objects is not zero. It's a tiny, 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 but finite number.
All right, and then Christian, is just a little bit of an alchemist question. If you can make gold in a lab through a nuclear reaction, is there any possibility, any prospect of mass production?
Oh, I smell a business opportunity here. We should do that. We should go ahead and do that. Now, the short answer is you can do that. You can produce, people produce gold out of something that's. The problem is that the energy you need to do that, to run an ion accelerator, is so much more expensive than the few atoms of gold you get out, that it's probably not a good business idea.
All right, so your profit margin will be negative.
Exactly.
Once you pay the electricity bill. Colleagues, I'm going to just check one last time before I release our speaker. Any last question or any last comment from anybody in the room? Auditorium, are we all happy?
We're good.
There's just somebody wanting to know whether there's any exchange programs at the Triangle University's nuclear lab for people to come and spend some time there with you and learn more about this fascinating world.
The exchange programs are not with the lab, but we have three very large universities that run the lab. Duke University, University of North Carolina, where I am, and North Carolina State University. So the best would be to enlist in exchange programs through the universities. There are lots of different exchange programs. So we do have people, I had people who from Europe and elsewhere who worked with me over the summer or over a semester, or they even entered grad school and did their PhD with us. But that's the best way of doing it.
All right, Christian, it doesn't seem as if there are any more questions. But again, thank you for your time. Thank you for sharing your knowledge and your expertise, and just reminding us that there is still value in doing science for the sake of science. Because as we do that, there's a development of skills, and we can still unravel and answer some of these questions that we still have unanswered. But thank you for your time, and thank you for taking us on this journey and just reminding us that this has been a long process, but there's always something new to learn. To all of you who are online, thank you for joining us this evening, and we will let you know when we have our next public lecture. Thanks again, Christian. Have a good evening. Or sorry, you still heading into the day. We're going to head into the evening. But thanks again for your time.
Thank you, everybody. Thank you for participating.